Hello, students, and welcome to Integrated Math 1, Section 812, Multiple Representations of Exponential Functions. We'll be in the book on page 437, and I just want to zoom in on this diagram right here. That's worthwhile taking down in your notebooks. Our focus will be to learn how to represent exponential functions from an equation to know what each of those pieces represent, and how to identify those pieces in the equation when you have a table in front of you or a graph or a situation. So the game plan for today is for us to work a couple examples together. So we'll start with 8-21A and B, and then give you some time to work individually and close out as a team. So let's start with 8-21A. And if at any point you need to pause this video and rewind for the class, please feel free to do so. Everyone should have their notebooks and calculators readily available, so let's dive right in. Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of this table is shown at the right, but we're missing some important pieces. We're missing the data for bounce number 0, or the initial drop height. And again, after one bounce, we're missing the height. So we need to find the rebound ratio. So let's start there. If you recall, the rebound ratio is simply how high the ball bounces after one bounce divided by its previous height. So we're going to start with that. That rebound ratio. I'll just call it R squared, if you will. Not the same as that correlation coefficient value or variability, by the way. All right, so again, we're going to take the bounce height, and we're going to divide that by the previous height. So for us here, we just need two consecutive numbers. So we'll take this height right there, 67.6, and divide it by the previous height before that, which was 84.5. And if you do that on your calculators, you're going to get a rebound ratio of 0.8, or 80%. So what that means is the ball is bouncing up 80% of the previous height that it just was beforehand. So I would expect to get the same number if I did 54.1 divided by 67.6. That should be 80% as well. So now that we know that piece of information, we can think about working this table backwards to figuring out what are these missing values. We could also write an equation to represent this data. Okay, so let's find how high that bounce was after bounce number 1, or X. So we can think about it this way. Working our pattern forward, we are multiplying by 0.8. So if we want to work it backwards, we really need to divide by 0.8. Because remember, exponential functions, they're really geometric sequences where we're multiplying from term to term. So let's go backwards and divide. So 84.5 divided by 0.8 is going to give us 105.625. And that's what's going right there. Again, we're going to take 105.625 and divide that by 0.8. And that will give us 132 approximately. Okay, so we found the missing pieces by working our multiplier backwards using division. And what we have now is the initial height right here of 132 centimeters. And we also have our multiplier. So when they ask us to write an equation to represent this, we'll start with that initial height of 132, our multiplier of 0.8, and raise that to the x power, and that will be our exponential equation for this situation. Let's take a look at part B. Okay, in part B, we've got a major tech company. Expo is growing very fast. They've got the number of employees is represented by the y variable, and they have an equation to model their situation right now. Here it is. X represents the number of years since the company was founded. So remember, Y employees, X years since they were founded. We just need to answer, looking at that equation, how many people founded the company and how can the growth of this company be described? So if you remember the previous example, that first part of our equation was that drop height. That was where we begin. That's your y-intercept. So in this equation, y equals 3 times 4 to the x. This is also where we begin. Or in this situation, we can say 3 people founded this company. How is this company growing? Well, look no further than our multiplier right here. This is how we are growing. Sometimes you're growing, the number's bigger than 1. Sometimes you're decaying, like in the last example, if the number's between 0 and 1. But we're growing here, and that is times 4. So we are quadrupling every year. So we're going to write down, we're growing by a multiplier of 4 each year. So remember those basics when looking at an equation. That first number is your y-intercept. It's where you start. And that second number, that's your multiplier. It's how you're growing or decaying. All right, now some opportunity to try some of these on your own. Let's go take a look at the next example. In 21 parts C and D, what I'd like you to do is I'd like you to quietly or silently read the example to yourself and try these individually. Remember the previous examples and what the equations look like and what those parts and pieces mean. How did we find the multiplier? That rebound ratio. Remember, taking one number divided by the previous number. Use that information to tackle part C and parts D here. Good luck. Pause the video and unpause it when you're ready to go through the answers. All right, let's take a look and see how you did at 21C and D. So the first question in C was how many computers are in the technology center? Well, that would be where you start at day 0. There are 27 uninfected, so that's how many computers there are to begin with. The next question, what portion of virus-free computers is infected each day? So the population of uninfected computers is decreasing, right? There's a multiplier of 2/3 happening here. So that means 1/3 of the population is becoming infected every single day that passes by, if only 2/3 of the population is remaining uninfected. And finally, using that pattern, we can continue the trend to day 3 to calculate there would only be 8 uninfected computers remaining at the end of day 3. All right, part D wants us to revisit Expo Grow. And when we do, we discover there's 5 founders. So that starting value in your equation is 5. And the multiplier is now doubling. And so that would mean times 2. So there's your reworked equation if those were the actual values. All right, to close things out today, work as a team on 822 and 823. 822, you're breaking down your understanding of what the parts of the exponential equation y equals a times b to the x mean, and where you can find those pieces in a table and in a situation. In 823, you're revisiting that multiple representations web. So take a look at that and close that out as a group for the last 10 minutes of class or so here. And then finally, make sure you revisit the target. Can you use multiple representations of exponential functions? And be sure to take a look at your next steps, which is going to be some homework practice, homework number 79. All right, students, good luck and have a great night.